So in the previous section, we saw how TCP comes up with some random number, usually it's some monstrously huge number, as its initial sequence number. And then as it starts sending data, it counts every single byte in that particular segment, and whatever the sequence number of the last byte is, so it takes that beginning sequence number, adds 1 to it for the first byte, adds 2 to it for the second byte, and then whatever the last byte is, whatever that byte number is, that's going to be the sequence number of the next segment. Now, we've really been paying attention to the sequence numbers. Let's talk a little bit about acknowledgements for just a moment. When you're first learning about TCP, a lot of people are under the impression that it works somewhat like this. That some data goes out, I'll just say data segment number 1, and then an acknowledgement comes back. ACK for segment number 1. And then another data segment goes out. Let's say data segment number 2, and an acknowledgement comes back for that. ACK for segment number 2. Okay, there's actually 2 things wrong with this diagram. First thing that's wrong is this. We know that from the way I've described it earlier, the way that it works in the background is that TCP can only transmit, whether it's transmitting a segment or whether it's transmitting an ACK. It can only transmit anything when the CPU says, okay, I'm done with this process, I'm done with this process, now it's time to give TCP a little slice of my time. So the CPU can say, okay, TCP, it's time for you to transmit. Go. You've got these few milliseconds to go, or these few microseconds to go. So now at that point in time, until the CPU got to TCP, he may have been building a segment, building a segment, building a segment, and buffering all these segments. So the first thing is, when TCP actually gets the opportunity to go, there's a very good chance it's going to send more than one segment within like microseconds of each other. So I'll just put here number 2, number 3, and number 4. So that's the first thing to realize. Second thing, if you assume that each one of these segments is going to produce an individual acknowledgement on the receiver, well, that could happen, or it might not happen. This is really up to the receiver and up to how the process is written. Most applications, what I've seen is they'll do one of 2 things. When they very first start the communications, yes, it'll be 1 for 1. So if I'm the, let's say that I'm the client, so that server has just hit me with 4 segments. Let's say, bam, 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 4 segments I've just received within a few milliseconds of each other. All right. So now when my TCP process and my client gets activated, I say, okay, here's 4 segments. Now, initially, I might say, okay, I'll create an acknowledgement for segment 1, an acknowledgement for segment 2, segment 3, and segment 4. And now my CPU might say, go, and then I'll send out all 4 of those acknowledgements, 1, 2, 3, 4, on the wire. So it might start like that. But usually what happens is within a very short amount of time, sometimes even immediately, what will end up happening is one single acknowledgement will go out that will actually acknowledge more than one segment. So for example, let's say, going back to what we were looking at before, that this first segment had a sequence number, let's just make it easy, of 1, and it contained 20 bytes of data. Okay, so that means that byte number 1 would be sequence 2, byte number 2 would be sequence 3, so each byte is being added onto this. So we would expect the next sequence number to be 20 plus 1, or 21. Let's say that also had 20 bytes of data. So then this next one would be sequence, so it would be 21 plus 20, which would be 41. Let's just stop it there for a moment. So what you might see, it's in very likelihood, is that you might see one acknowledgement which would say 41, meaning I've received, and this would implicitly saying I've received all of these bytes. So the first byte in this one was byte number 21. Remember, we take the sequence number and then we add it. So we add 1 byte to that, 2 byte to that. So the very first byte was 21, then 22, then 23, then 24. So this is saying I received up to byte number 41, which was the very last byte in the second sequence. So a lot of times you'll see that, where processes will decide, okay, instead of sending a single acknowledgement for each segment I've received, I'm actually going to send one acknowledgement for every 2 segments I receive, or one acknowledgement for every 3 segments I receive. And this has its positives and its drawbacks. So clearly the positive is, let's say I'm the client and I'm receiving 10 segments. It's probably easier for my CPU to create just 2 or 3 acknowledgements to cover all 10 of those segments, or maybe even just 1 acknowledgement to cover all 10 of them, than to create 10 separate acknowledgements, each one with its own TCP header. So now each one's going to have its own IP header 10 times. So from the perspective of the person who's generating the acknowledgements, it's easier that way. Easier to create one acknowledgement that acknowledges multiple segments. The downside really is, though, for the sender. And towards the end of this, when we get into congestion control and slow start, we're going to see that. But most TCP implementations, the way they work is they start slowly. In other words, they might start by saying, okay, now that my 3-way handshake has started, I'm going to start by sending like 3 segments. And then if I get acknowledgements back, I'll send 6, and then I'll send 12. Well, a lot of times the way that works is, if I send you 3 segments, if I get 3 acknowledgements back, if you actually do me the courtesy of acknowledging each segment individually, I'll say, oh, okay, well my algorithm says for every acknowledgement I get back, I will increase the amount I can send by that number. So if I send you 3 segments and you send me 3 acts back, I can say, okay, my window was 3, now I got 3 acts back, so I can say 3 plus 3 is 6. Now I can send you 6. And if you send me 6 acknowledgements back, now I can send you 6 plus 6, which is 12. But you can see, if what you're doing is you're saying, okay, for every 4 segments I send you, you're only sending me 1 act back, how does that affect me? That means I can't ramp up as quickly now. The quantity of segments I can send to you at any one time is not as fast if you're not acknowledging each and every segment. So we'll go into that in more detail. But the main takeaway I want to start this section with was that don't be under the assumption that for every segment sent, an individual acknowledgement will come back. That might happen, but usually it's not that way. In most of the sniffer traces I've seen, it's like 2 for 1. For every 2 segments that go out, a single acknowledgement comes back. That seems to be pretty standard. Okay, so we're going to have to introduce some new terminology that we're going to talk about in this section. I'm going to go through all these in detail, but in this section we're going to talk about something called the retransmission queue, the RTO or retransmission timeout, the smooth round trip time, or sometimes it's called the round trip time, and something called the timer backoff. These are all going to be things that are related to acknowledgements and when I retransmit a segment if I decide to do so. Okay, so let's start with the retransmission timeout. And what is that? So the retransmission timeout is a timer that says, okay, once I send a segment, I'm going to start this timer called the retransmission timeout. If I do not get an acknowledgement for that segment, or some acknowledge that at least, maybe an acknowledgement comes back that acknowledges 3 or 4 segments that I sent, but before this retransmission timeout expires, I need to get back something that says he got this segment and all the bytes in here. If the retransmission timeout expires, well, guess what? That tells me I need to retransmit that frame. That's just like it sounds like. Now, how does TCP determine the value of this? Well, when you very first start a connection, at the very beginning, it says, well, I'm just going to pick some default value. And this is really operating system dependent. I did a little bit of research, and Microsoft's TechNet website says that they use 3 seconds as a default. So at the very beginning of a session, TCP in Microsoft Windows anyway starts out with an initial RTO value of 3 seconds. But it doesn't stay that way. And I'll talk a little bit more about that as we come up here. Actually, no, I guess now is a good place to talk about that. So the retransmission timeout starts out at some value determined by the operating system, like let's say 3 seconds from Microsoft. And then what happens is, as I send something, like probably just my initial sync, I believe it just starts out with the initial sync and the 3-way handshake. So that very first sync, I start timing it. I say, okay, how long is it taking to get the ACK back? In other words, what is the round trip time? The time it takes from the time I transmit something till I get a response back from that. That's called the round trip time. And then the retransmission timeout at that point is tied to the round trip time. But here's the little gotcha, and I didn't put the formula in here because I think it's just way overkill. But the designers of TCP said, look, the round trip time could vary, right, depending on the conditions in the network or depending on the receiver, right? Maybe right now when I send my sync, the guy who's receiving that, he's totally free. Nobody else is talking to him. His CPU is kind of idle, so bam, he can create an acknowledgement and send it back to me in light speed. And the network's totally fast, so that's a real quick round trip time, maybe 20 milliseconds. But the next time I send my next segment, maybe it's totally different. Maybe all of a sudden when I send it to him in the intervening time, he's just had like 200 connections connect to him, and now it's taking him quite a bit longer to send that ACK. So whereas the first one had a 20 millisecond round time, maybe the next time has a 50 millisecond round time. Or maybe conditions in the network have changed. Segments have been directed down different paths due to routing protocol changes or whatever. So the designers who designed TCP, they said, you know what? We don't want this retransmission timeout to be bouncing all over the place, really big, really small, really big, really small. We want it to sort of be, it's okay to change, but not change that dramatically. So if you actually look in the specification, I didn't put it in here, basically what they did is they take that round trip time of the very last segment, and they say, let's do it this way, they say, okay, my very first sync plus ACK, what's that? Oh, that's 50 milliseconds. Okay. So right now, I'm going to assume that is the round trip time. Now, the next segment I send out and get an acknowledgement back, maybe that's 30 milliseconds. So they basically take those two and they plug it into a formula. And it's kind of a nasty formula, but it sort of comes out with a smooth average. It's not an exact average of round trip times over time, but it takes the most recent round trip time, compares it to the last one, looks at the difference, multiplies it by some multipliers and other variables, and it comes up with what's called the smooth round trip time, because it's kind of smooth. Instead of being spiky like this, it tries to smooth it out. And the smooth round trip time is what the RTO value is based off of. So this retransmission timeout is directly linked to how long it takes to get something and then get an ACK back. It's all based on that. Okay, so every segment transmitted by TCP is copied and placed on a retransmission queue, because this makes sense, right? I mean, if the application put, let's say, 50 bytes into a buffer, and then TCP said, okay, I'm going to take out the buffer, put in a segment, and away it goes. And now my client forgot about it. Well, how could I retransmit that thing if I never got an ACK? I have to keep a copy of it. So there's this thing called the retransmission queue. So for all the bytes that TCP sends, it places those bytes into a retransmission queue, and it waits for those bytes to be acknowledged. If an ACK is not received by the time the retransmission timeout expires, then that segment is kept in the retransmission queue, but a copy of it is now placed into a segment and sent out. Because once again, let's say we retransmit that for the first time. Maybe that retransmit also will not get an acknowledgement. So we have to keep that copy of those bytes in the retransmission queue until one of two things happens. Either we get an acknowledgement And once we get an acknowledgement, we can say, okay, great, remove that from the retransmission queue. I don't have to remember that anymore. Or TCP will eventually give up, right? TCP will say, look, I've retransmitted this thing X amount of times. It's still not getting acknowledged. At that point, I'm done. Erase it from the retransmission queue and inform the upper layer process that these particular bytes I couldn't send. Now you might be wondering, well, how often does that happen? How many retransmits have to occur before TCP gives up? We'll get into that. That'll be at the very end of this video section right here. I'll talk about that. And subsequent retransmission timeout values are determined by the smooth round trip time. That algorithm smooths it out. Okay, so here's an animation to sort of just show all this. TCP segment number 1 is created. He says, I'm starting a new connection, so I'll set my initial round trip timeout to 3 seconds. Now, if you're dealing with Linux or Unix or Apple's iOS, it might be some other default value. It might even change between Windows 7 and Windows 10. It's completely up to the operating system. Okay, so he places a copy of all those bytes in the retransmission queue, remembering that sequence number, and now he takes a segment, sends it on its way. Now, he starts counting. 1 microsecond, 2 microseconds, 3 microseconds, he's counting. Now in the meantime, the server said, oh, I need to create my own sync and ACK. So he creates that, sends it on its way, and he starts counting. In the meantime, the client says, oh, here comes my sync plus ACK. So it took 50 milliseconds for that, from the time I sent my sync until the time I got the sync ACK back was 50 milliseconds. So I'm going to run that through my formula and come up with some number. This is just an estimate here, but come up with some number close to that, in this case 55 milliseconds, to be my retransmission timeout. Now look at the server on the right. He's going to do the same thing. He just sent out his first packet segment. So he is going to start counting. 1, 2, 3, 4. Eventually the ACK comes back and same thing. He says, all right, that took 50 milliseconds and I'm going to say 54 milliseconds is my retransmission timeout. Okay, now notice this. The initial retransmission timeout. Start out some number. If it expires, it makes sense. Let's go ahead and retransmit that frame, that segment. But not only that, look at that. The retransmission timeout is doubled for that connection. If that segment we just retransmitted, if that doesn't get ACKed, guess what? We double it again, and we double it again. So every time we have to retransmit a segment, the retransmission timeout keeps getting longer and longer and longer. In other words, we're giving more and more of a grace period for that acknowledgement to come back before we decide to retransmit it. Now, the technical term for this doubling of the value is called the timer backoff. We saw that at the very first slide of this section, timer backoff, and that's what this is, that process of taking the retransmission timer and doubling it, because we're not getting ACKs to our retransmissions. That's the timer backoff. All right, now here's what happens. So a segment goes out, oh, it's lost. Congestion, segment was dropped. Now right now the server's saying, okay, my retransmission timeout was 54 milliseconds. I sent out the segment, I'm counting down, 54, 53, 52, 51. Eventually he counts down to 0. Okay, no ACK. So now I'm going to double my retransmission timeout. It was 53 milliseconds. Now I'm going to double it to 106 milliseconds and retransmit that segment and send it out again. Now once again, as far as operating systems are concerned, I read this on the Microsoft website. Can't say if it applies to Apple or Linux or anything else, but Microsoft's website says, look, if for some reason the retransmission timeout value gets all the way up to 240 seconds, think about that, that's 4 minutes. If it gets up to 240 seconds, at that point, stop incrementing it And if I have to continue retransmitting that frame, hold it steady at 4 minutes. Now you might be thinking, well, wait a second. If my initial sync and ACK was, let's say, 75 milliseconds, which, it's probably about average. If I had to double that once, that would have been 150 milliseconds. If I didn't get an ACK and doubled it again, that'd be 300 milliseconds. How many times would you have to double that before you got to 240 seconds, which is what, 2,400 milliseconds, something like that? What this is for is really slow speed links. Like, let's say when you did your initial sync, you're doing it over a 56K modem, or you were doing it over a really slow satellite link. And it actually took you 45 seconds from the time you sent the sync to get the sync ACK. So your very first round trip time was some monstrously huge number right out of the gate. Well, if that's the case, it's only going to take like 2 or maybe 3 transmissions before you hit 240 seconds. According to Microsoft, it says, look, if you actually get that bad and we're still allowed to retransmit, hold it at 240 seconds. Of course, that would be pretty horrible to get to that point. Now, this brings us to our very last question. When do you give up? How many times do you have to retransmit this thing before you realize it's just not going anywhere? I'm just not getting my acknowledgement. So after a predetermined quantity of failed retransmissions, TCP will give up. And guess what? That is also dependent on the operating system. It does not say in the TCP standard how many times it should wait. They leave that up to the vendors. But in case you're curious, Microsoft Windows has that timer called the TCP Max Data Retransmissions, which defaults to the value of 5. So if after 5 retransmissions you don't get an ACK, you're done. Strip it off the retransmission queue, let the upper layer application know that it failed. This is actually configurable. I actually found a website somewhere that talked about how you can go to regedit and change that if you want to bump it up or bump it down. So it is a configurable value, but that's the default value. And as far as the timers and everything that we've talked about in this session, if you're actually curious about like what the formula is, how's it come up with this smooth round trip time, and how's that formula actually work to come up with a retransmission timeout? If you actually want that level of detail, I'd recommend you go into RFC 2988, 2988. So RFC 2988 gives you all those formulas and goes into all of that. So up until this point in time, what we've looked at is the assumption that a segment goes out and an acknowledgement for that segment comes back. Or maybe 2 segments go out and an acknowledgement comes back acknowledging both of them. What we're going to look at next is what happens if I send 4 segments, I get an acknowledgement for the first one, the second one gets lost. What about segments 3 and 4? How does the receiver deal with that? And we're going to talk about that in the next video.